Welcome back everyone. This is the Q&A session 21 from the playlist of laws of motion. The topic is work energy theorem, and I have taken here one question which was asked in one of the medical entrance examination long time back. So here the question is, the upper half of an inclined plane is perfectly smooth and the angle of inclination is theta. So this is the figure which I have already drawn here. So here this is AC is the inclined plane, and the upper half of this inclined plane is perfectly smooth, that is, it is frictionless. The lower half of this inclined plane is rough, and there is a block which slides the inclined plane, which slides down the inclined plane from rest and comes to rest at the bottom. So this is the bottommost point of this inclined plane, which I have depicted here with C. So this is the bottommost point here. So the block which is initially at rest at the topmost position of this inclined plane comes down to rest at the bottom by sliding. So the coefficient of friction is, there are four options here and we have to find the correct one. So here we will be using this work energy theorem in order to solve this question, and this is going to be solved in a couple of steps. So as per the work energy theorem, the change in the kinetic energy of a body is equal to the sum of all the sum of the work done by all the forces which are acting on it. So here the change in the kinetic energy, of this block is 0, because its initial at the topmost point of this inclined plane, it is at rest, and it slides down this inclined plane and comes to the bottom most point to rest. So at this point also it is at rest, at the topmost point also it is at rest, so the change in the kinetic energy is 0. Now we have to calculate the total work done by all the forces acting on this block. So the total work done will be equal to the work done due to the gravitational force plus the work done against the force of friction. So the total work done in this case will be equal to the work done due to the gravitational force plus the work done against the force of friction. So we have to first of all find the work done due to this gravitational force. So here this the weight of this block is acting vertically downward. So I have resolved this into two components, that is mg sin theta, which is acting along this inclined plane in the downward direction as indicated by this arrow, and the other component, that is mg cos theta, will be equal to the normal reaction. So here the work done due to this gravitational force, which I am just writing here as Wg, this will be equal to the force multiplied by the displacement. So here in this case the displacement will be equal to L. So this will be equal to mg sin theta into L. And now here this work done will be positive, because the work done is positive if the direction of the displacement and the force, means that is the force and the displacement are acting in the same direction. So in that case the work done is taken as positive, and the work done is taken as negative if the displacement is in the opposite direction of the applied force. So the work done due to this friction will be equal to mu mg cos theta. So this is what mu mg see here mg cos theta is a normal reaction, and mu m, here the work done is equal to force into displacement. Now force, that is the force of friction, and this force of friction will be equal to mu mg cos theta, and d is the displacement. So displacement in this case will be equal to L by 2, because the force of friction it comes into play in the lower, that is in the lower half of this inclined plane. So the total work done now will be equal to the work done due to the gravitational force, which is equal to mg sine theta into L, and this is going to be mg sine theta into L into mg sine theta into L, and this is going to be positive, and the work done against the force of friction is equal to mu mg cos theta into L by 2, and this work done will be negative because here the displacement is in the opposite direction of the force of friction. So now this total work done will be equal to the change in the kinetic energy, which is equal to 0. So if I equate this from this equation, that is mg sine theta dot L, this is now equal to mu mg cos theta into L divided by into L by 2. So from this equation, I will be getting the relation, that is g sine theta is equal to mu cos theta upon 2, or we can say that this cos theta can be we will divide this equation on both sides by cos theta, so I will be getting tan, that is g tan theta. This will be equal to mu upon 2, or we can say that mu is equal to, sorry, this is equal to mu cos, this is equal to g into g, yeah. So from here this g and g will get cancelled out, so we can say mu will be equal to 2 tan theta. So the correct option here is A, that is mu will be equal to 2 tan theta. And in this question, the only important thing was the application of this work energy theorem. So thank you very much for joining this session. In the next session, we will be coming up with a different topic, which will not, it will not be the top, I will not be taking the question from the work energy theorem. It will be from some other topic, and but that chapter will remain the same, that is laws of motion. So till then, have a nice day, bye.